One of the reasons we started this chapter by looking at one-to-one functions and at inverse functions is because of 5.4, logarithmic functions. A logarithmic function is a new function that we're going to use to find the inverse of an exponential function. If you remember last section, our exponential function looked like this. And you see that our exponential function is a one-to-one function. It passes the horizontal line test. So it would make sense to ask, could we find an inverse for y equals 2 to the x? Step 0 is check to make sure it's one-to-one. It is one-to-one. Step 1 is swap out the x's and y's. And step 2 is to solve for y. But how do we solve for y when y is in the exponent right here? Well, the answer is we have to use a logarithmic function. So what we do is we write the log base 2 of x is equal to y, and that solves our problem. So this is our definition. In order to rewrite this in this form, we kind of have a log base 2. If I do 2 to the y equals x, so you have 2 to the y equals x. So this allows me to solve for y, or solve for my exponent. So if we run into a question where we need to solve for an exponent, for example, if we have 5 to the x is equal to 25, we can use our techniques from last section to match the bases if we'd like, or we could write log base 5 of 25 is equal to x. So again here it's 5 log base 5 of 25 is x. So again we're kind of going like that. 5 to the x is 25. So we can go back and forth in between exponential form. So this is exponential form and this is log form. We're going to want to go back and forth between exponential form and log form depending on what the question gives us. For example, if we have log base a of 4 is 5, then we would want to know what a is. So we can go from log form to exponential form. A to the 5 is equal to 4. Again, that's a to the 5 is 4. You kind of have a fish hook here. I've heard that called before. So a to the 5 equals 4 is something we can solve. We can take the fifth root of 4 in order to solve this. And there you have your solution. A equals the fifth root of 4. We can find some exact values. So if I said log base 2 of 16 equals x, we can, if we don't know what log base 2 of 16 is, we could try to rewrite it in exponential form. That is 2 to the x is equal to 16, and then use the techniques for solving exponential equations that we learned last time. Match the bases. 2 to the x equals 2, 4, 8, 16. 2 to the 4 is 16. And then from there, x must equal 4. Another example is log base 3 of 1 over 27. Now we should note that log base 3 of 1 over 27, log is a function, like f of x is a function. The name of our function is called log base 3. So if I've got things outside of the function, they can't interact with things inside of the function. This is the argument of our function. So if I want to solve this, I can rewrite it in exponential form. 3 to the x is equal to 1 over 27. Then the question is, can we get the bases to match so that we have 3 to the x equals 3 to the power? And the answer is yes. 27 is 3 to the third. Since it's in the denominator, we could write it as 3 to the negative third like so, and then x equals negative 3. So then you may be asking yourself, great, is there anything else we can do besides solve equations? And the answer is yes, and we'll do that next.